This is part 4 of the course, where we talk about abelian groups. And I should say abelian groups not in isolation, but about abelian groups and number theory. So we will discuss a few topics related to number theory in a little more detail, and relate them to things we already know about groups. And I want to start with the first part about cyclic groups. So of course, this is a very fundamental topic, and maybe I should have done it in the beginning of the course, but somehow we postponed it until now, though you have already seen these objects. Okay, so also I should say that I assume some knowledge of arithmetic, like division with remainder, then things like divisibility, and co-prime numbers, in general greatest common divisor, and prime numbers together with fundamental theorem of arithmetic. So I assume you know these things. If not, please maybe look them up before. Also modular arithmetic. So we already discussed it a little bit. So I will review some bits of these things and discuss them from group theoretic perspective, but I very seriously recommend you to first get some more down-to-earth, more elementary understanding of these topics, and only then proceed with group theory approach to this stuff. Okay, so let's start somewhere, and I want to start with discussing subgroups of Z. And by Z, I mean, of course, Z is a group by addition, and the question is, okay, what are all its subgroups? So, little proposition, but very important, is that any subgroup let's say H inside Z is of the form NZ, where n is greater or equal than 0, and of course by this I basically mean all numbers divisible by n. Okay, so this is something you probably understand very well. Even numbers divisible by 3 and so on, all are subgroups of Z. In particular, also, if this is true, obviously H is isomorphic to Z, so every subgroup of Z is isomorphic to Z. Such a simple picture. By the way, it's an interesting example when you have a subgroup which is isomorphic to the whole group, and of course that can happen because Z is infinite, so there is nothing wrong with it, and this is the case here. Okay, proof. Very classical idea. So, so if H equal to 0, take n equal to 0, and clearly it's unique, and so there is no question. Okay, so assume H is not 0. H is not equal to 0, and by 0 I mean the subgroup which contains just one element, 0. So that's kind of the shorthand for this one. And assume H is not 0, so let n be the smallest positive element of H. So there are two questions: why there exists any positive element, and why there exists the smallest one. So H contains positive elements because H is not equal to 0, so suppose maybe some number m is contained in H where m is not 0, and so if m is, so either m is positive or minus m is positive. So positive elements exist. So H intersect positive integers is not empty. And then the fact that there exists a smallest positive element is a reformulation of induction principle. It's called minimal element principle. Every subset of positive integers has the smallest number. And one can show that this is equivalent to induction. So let n be that one. So claim is that, of course, H is this nz. Okay, why it's the case? So obviously nz is inside H, and the reason is just because n is inside H, you multiply it by any number, it's inside H. And then let's assume, so if some element H is inside H, so then one can divide by n with remainder. So there exists Q and R such that H equal to nq plus R, this is H, and R is less than n greater or equals than 0. So absolute value of n usually, but here n is positive. And then of course it implies that R is a difference of two elements in H, R is in H. And that leads to a contradiction because we have an element, so it is an element less than n inside H. We took n smallest positive element, so then R is equal to 0, and this implies that H is inside nz. So that finishes the proof. Okay. So now we know all subgroups of Z. Okay, next thing. So we have this Z, and it contains nz. And of course, this nz is normal there because everything is abelian. So what it means we can form a factor group Z mod nz. And this is, of course, remainders modulo n. And now you know that this remainder story is actually a special case of this factor group construction. You can take the quotient and elements there are cosets, and cosets of course are exactly remainder classes, equivalence classes, modulo divisibility in n. So nice. And then let me just remind you this definition. So a group G is cyclic if and only if G is generated by one element. Okay, so if and only if G is generated by one element. So very important proposition, very simple proposition, but very important is that so G is cyclic, then G is isomorphic to Z, or G is isomorphic to Z over nz for some n greater or equals than 0, we can say. Of course, when you factor by 0, you can divide by 0 in this game and you get just Z back. Actually, maybe I should say, so to make them all distinct, let me say greater or equal than 1. Okay, so and proof is very simple. So proof. So assume that G is generated by one element G. And then let's look at all elements E, G, G squared, and so on, G inverse, and so on. So these are all elements in G. And then there are two cases. So case 1 is, so all these elements are distinct. And this is, of course, this immediately implies that G is isomorphic to Z. The isomorphism sends G power k to k. Product goes to product, that's just rule of multiplying powers. That's a bijection, nothing to check. Okay, and case 2 is, this is not true. There exists, let's say, n less than m, such that g power n equals g power m. So then, of course, g power m minus n is equal to identity, and g has finite order. So finite order means some power is equal to m minus n. Okay, so let's take the order of g, and I remind you that this is a number, this is a minimal number of all k in integer, such that g power k equals to the identity. And if you want order to be infinite, you can take maybe union with infinity. And we already discussed that. And let's take this order. So in our case, it's finite, so less than infinity, because we assumed that this is the case. And then, okay, so let's denote it by d, and then actually e, g, and so on, g power d minus 1 are different elements, and then they start to repeat. So this is g power d plus 1, and so on. And so it is really easy to see that then, of course, g power n equals 2. So if you just divide n on d with remainder, if n equals qd plus r with r less than d greater or equals than 0, then this is the same as g d power q times g power r, which is g power r, and so every element is one of the list. So basically, the whole group G has these elements E, G, and so on, G, D minus 1, and these elements are distinct. So why they are distinct? Because imagine they are equals, and you can divide one by another, and you get that even smaller power than D is identity. And then, of course, you just construct this isomorphism. You just take this, you construct this isomorphism from G to Z over DZ, sending G power N to the remainder class of N. That's the corresponding isomorphism. So we have already discussed it a little bit, so this is just a little reminder. Maybe one thing to remember, which is kind of obvious from the statement here and this argument, is that if, let me maybe formulate it actually. Okay, so maybe some properties of the order of G. So this is again something we maybe should have discussed much earlier, but still. So first one is that, so we have the setting, you have a group and some element G inside, and assume that the order of G is equal to D, some finite number. So then G power N equals to the identity implies that D divides N. And that's again, so proof is divide with remainder. So the same trick, assume G power N equals to identity, divide N by D, and then G power remainder is equal to identity. And if N did not divide D, if remainder is non-zero, then you get some smaller number so that it has identity, and this contradicts the definition of the order. And another thing which is kind of important, so let's assume that I'm interested in order of G power K. So what is that? I mean, obviously it might be N, but it might be smaller, because it might happen N is not prime, for instance, and maybe K already has some kind of multiple there which is contained inside N, and then smaller power works. And so the answer is that it is N divided by N comma K, where this is the greatest common divisor. That's my notation for the greatest common divisor. So the proof is again straightforward. So proof is really easy. So how to show that that this is the case? So the fact that this g power k power n divided by the greatest common divisor, that's of course equal to g power n power k divided by the greatest common divisor. And remember, this number are integers, and this is, sorry, by n I meant d, of course. D. And this is of course identity, because g power d is identity. So what it means that by the previous result, we know that the order of this g power k definitely divides d over dk. Okay, that's good. That's one result. And now I want to show the opposite. Okay, so let's assume, so suppose g power k power m equals to the identity. So suppose m is some number so that this power equals to the identity. Then of course g power k m is identity, which implies that d divides km. But you know, if d divides km, you can divide simultaneously both parts on the greatest common divisor. So then, of course, d divided by dk, which is again an integer, so you should be careful here, it's an integer, divides k divided by dk times m. Okay, and now these two numbers are co-prime, because we just divided them by their greatest common divisor. And since they are co-prime, we know that a product of, so if these two numbers are co-prime and m times k over d over k is divisible by d over d over k, it means that m is divisible by d over d over k. So this implies that m is divisible by d divided by the greatest common divisor. And hopefully we are done, because now we know that for every number like that, this is true. So in particular for the order of g power k. So it implies that d divided by the greatest common divisor divides the order of g power k. But when we have divisibility in both directions, and these are positive integers, you conclude that they are equal. Of g power k equals to d divided by the greatest common divisor with k. Perfect. So let's remember that. And now I want to say a few other things about cyclic groups. Okay, so the next proposition is very simple again, and this is a subgroup of a cyclic group is cyclic. So, okay, let's discuss that. So we have a cyclic group, so G is cyclic, and then there are two cases. So G is isomorphic to Z, then we know it, we know that was the first result today before. And then there is a case G is isomorphic to Z over NZ. And here, I mean, of course, you can prove it directly. That's quite a simple statement. But on the other case, we can also use correspondence theorem. So let's just recall, because I just want to practice maybe with correspondence theorem. So I know that I have Z, and inside I have a normal subgroup NZ. So what subgroups are in between? So so let me kind of say that. So subgroup of Z containing NZ are H equal to MZ, but of course not for all M. So imagine these are like numbers divisible by 2, numbers divisible by 6, and then they're contained in a subgroup of numbers divisible by 2. So with N with M dividing N. That's always a little bit confusing. So basically this subgroup NZ is here, and over it we have all subgroups of type MZ containing it. Like 2NZ and so on. Wait. No, on the opposite. Like MZ contains subgroup 2MZ. Okay, so, and then we can say that we have this factorization map from Z to Z over MZ. And we know that there is this bijection between subgroups. So this will correspond to subgroup 0. And MZ will correspond to some subgroup, let me denote this projection by P as I used to subgroup P of MZ inside here. And this is one-to-one correspondence. So what is this P of MZ? So clearly this is image of all elements MZ. Sorry, this is NZ. And let's now assume, so I know that M divides N. So let's assume that N equals to Km. And then what is P of MZ? So basically this P of MZ is just collection of numbers, remainder classes 0, M, 2M, and so on, up to K minus 1M. So this remainders, sort of remainders divisible by M. Though this notion of divisibility doesn't always make sense, but it does when M divides N. And so this is P of MZ, and clearly, okay, that's a cyclic group generated by this element. So this is isomorphic to Z over MZ. And we know that all subgroups come from this correspondence principle. So all subgroups here are images of subgroups of Z containing NZ, and we know that they are of this form. So the theorem is proven by that. Also, I want to emphasize the following fun idea. So there are two diagrams, two lattices we can draw. So we can draw numbers n where the ordering is divisibility. I'm sorry for the strange notation. That's divisibility, that's the ordering, and they are kind of the same. And I have another this Fratelli diagram for Z, all subgroups of Z, and I claim that they are basically the same. So let's just see that. So okay, so what is the smallest number is 1, and then we have all prime numbers which divide 1. So then we have all numbers which are products of 2 primes, and so on, and so on, and so on, and so on. In some sense, you can say up to 0. 0 divides everything. And here we have absolutely similarly 2Z, 3Z, and so on, 6Z, and so on, up to basically 0. So, and of course, here 2 divides 6, so So usually before we were, I think, saying that this is less or equal if 2 divides 6. And here 2z, 6z are, on the contrary, 2z is greater or equal than 6z. So you should think of these two diagrams as the same up to kind of reverting the this ordering. So basically you call elements greater or equal. So elements are greater or equal here if and only if they are less or equal here. But other than that, this is just the same diagram. So this numbers with divisibility is the same diagram as subgroups of Z, just because there is a kind of a bijection between them. Because all groups, subgroups of Z are nz for some integer n or 0. Okay. So that's interesting. So last thing which I want to, there are maybe two last things I want to discuss today. Let me start with just one remark about greatest common divisor. So I want to give you a group theoretic perspective on the greatest common divisor. So let's suppose we have Z, and let's take two numbers there, n and m. So if you have two elements of a group, you can look at subgroup generated by n and m. And sometimes for abelian groups, it's convenient to just write it as nz plus mz, meaning that these are all elements z times n plus z times m. Because for abelian groups, nothing can happen, nothing else can happen. You can always change order, put all n's in beginning and all m's at the end. For general groups, of course, you will have this reverse where n and m are kind of going one after the other. So this is a subgroup of Z, obviously, no question about it. And this is a subgroup, so literally this is just set of a n plus b m, for a and b being integer, all linear combinations. And then the question is, okay, it's a subgroup. So then there exists D in n such that the subgroup is equal to dz. Maybe n union with 0 for this weird case when both numbers are 0. And then the question is, what is this D? So D is this number, it's unique, as we explained before, and the statement is that D is exactly the greatest common divisor. So that's really easy to prove. So let's prove it. So assume that this is the case. So we know such D exists. So clearly D is a divisor of n and m, and the reason is because n and m are inside this dz, so they are d times something by definition. So now I want to show that actually D is the greatest common divisor. So why this is the case? Let's see. Okay, assume that D1 divides n and D1 divides m. So this is a common divisor. So if D1 divides n and D1 divides m, that means that the subgroup generated by D1 contains n and m. So then n and m are contained inside the subgroup generated by D1, which is this D1z. But then dz is contained there. So just because if two elements are inside some subgroup, the group generated by them is also there. So what it means that D is contained in this D1. But this means D1 divides D. And in particular, D1 is greater or equal than D. So any divisor is greater or equal than this D, thus D is the greatest common divisor. So this is interesting observation, and what is fun about it is that you can start playing this game without even knowing this concept of greatest common divisor. So if you know that every subgroup of Z is of type n times Z, you can start playing this game. Let's take a bunch of numbers, generate a subgroup. What is the element which is this unique generator? And this will be the greatest common divisor of a bunch of numbers. And various properties of greatest common divisor are very easy to see from here. So for instance, if you denote this D, so we denote it by nm, and then for instance, there is this property that greatest divisor of n and m is the same as greatest divisor of n minus m and m. And this is obvious because, just if you take this subgroups, so if you take the subgroup generated by n and m, it's just equal to the subgroup generated by n minus m and m. And the reason is, okay, these two elements are there, one of them is there, the other is the sum of these two generators, and vice versa, this one is a difference, this one is there. So the subgroups are equal, but then of course, this is dz, and then this is dz, and then the greatest common divisor is the same. So this is kind of a corollary, if you wish, but of course you might prove it using more kind of elementary number theory, but still. And then there is another corollary, which is a famous fact, is that so if n and m are integers, and D is the greatest common divisor, then there exist two numbers A and B in Z such that D equals to AN plus BM. And this is called the linear representation of a greatest common divisor. It's a linear combination of two numbers. That's a very important fact about greatest common divisor. And when you start kind of studying arithmetic, it might seem like a fancy fact or complicated theorem, or at least kind of why this should be true. From here, that's of course just the statement that D is inside the subgroup NM. So in some sense, this greatest common divisor has a dual definition. You can say that it is the biggest among divisors, or you can say that this is the smallest among elements, positive element among elements generated by A and B. And this happens to be the same thing. So that's kind of interesting. So final remark for this lecture. So we proved a lot of things and discussed a lot of things related to the integers, and in general all this arithmetic, prime numbers and so on. They are all based on division with remainder, and the fact that integers are not only a group but a ring. There are two operations, addition and multiplication. Multiplication is commutative, satisfies all basic rules. I will remind you them in the next lecture, but still. So that's a ring, and there is this division with remainder algorithm. And actually there are other rings with this property. So you can take Zi, which is a set of numbers a plus bi inside complex numbers where a and b are integers, and this is inside complex. And this is also a ring you can multiply and so on. You can discuss divisibility, prime numbers and so on, everything there, and more or less all the results will pass by. There are other rings like ring of polynomials over a field, and it's also a similar kind of ring. It satisfies an analog of division with remainder, and it has this prime elements which are indecomposable polynomials. It has this basically analog of fundamental theorem of arithmetic, greatest common divisor, just everything is kind of the same here. And what is the most remarkable maybe is that not all rings like that are like that. For instance, you can take a ring like Z with added cubic root of, I don't know, 17 or something like that, and ring like that, it won't have this property that there is this, I mean, there exist prime elements, but there is nothing like the fundamental theorem of arithmetic there. And So you cannot talk about greatest common divisor as an element, but you can still talk about this set. And later on in the next quarter, we will spend a great deal of time understanding ideals, and ideals will be exactly this kind of elements. And for Z, they correspond to actual elements in Z, but for other rings, it might be not the case. So this is the first instance of what will be called an ideal in a ring, and we will spend half of the next quarter discussing those and interesting arithmetic applications. Okay, so next lecture is about a ring of so this Z over NZ is a ring, and about Euler's function.